Okay, hello everybody. Today we're very happy to have Ido Ben-Dayan from Ariel University to tell us about the improved null energy condition. Please, Ido.
Thanks, Shachar, and thanks everyone for coming. It's a pleasure to give this talk in this gravity online seminar. So I will discuss a recent work of mine, which is the title is the improved null energy condition, or INEC for short, which was published recently, and some ongoing work in progress. So the outline will be very pedestrian, at least the beginning. I will describe, when I say general relativity and semi-classical gravity, what do I mean by that? And then I will discuss briefly something which is called the quantum focusing conjecture. Then what is this improved quantum null energy condition, and some sketch of a proof or how we're going to try to prove the condition, and then implications. Now, throughout the talk, you'll see various nice pictures which are not related to the talk. So if you get lost, then you can at least enjoy the nice pictures. Okay. So right in GR, in general relativity, basically we're equating geometry with energy. So, if we assume some metric like FLRW metric, black hole metric, gravitational waves, whatever, that fixes the left-hand side of the equation here, G mu nu, Einstein tensor. But what is fixing the right-hand side? And the right-hand side should be the energy momentum tensor, which describes the energy sources in your space-time, whether it's particle, fluids, black hole, cosmological constant, whatever. And many times, certainly in cosmology, we use this so-called fluid approximation where we say, okay, our energy momentum tensor is that of a perfect fluid. So it has the energy density rho and then the pressure in the spatial parts of the tensor. And it's diagonal. For a perfect fluid, you can always move to the rest frame of the fluid where it's diagonal. Okay. But GR doesn't tell us what are the allowed energy momentum tensors. I don't have a theory that tells me which energy content I have in my universe. And actually, I can use Einstein's equations in something called the Singe method, which is to construct any type of energy momentum tensors that I want. How do I do that? I pick a metric, GAB. I plug it into the Einstein tensor, and then into the Einstein's equations, and voila, I have an energy momentum tensor which has, any form. But of course, we know that in our universe, not every energy momentum tensor is reasonable or valid or even exists. So, right, one thing that we can say is that usually if we have degrees of freedom that propagate superluminally faster than the speed of light, right, we don't view these as physical or reasonable degrees of freedom. And that's not the only constraint that one can think of. So let us try to think what are plausible energy momentum tensor, what are plausible energy momentum contents. So a simple way to look at it is, so this is because I'm coming from cosmology, this is the way, which is the simplest way for me to present it. So if we consider the fluid approximation, so I have an equation of state that relates the pressure to the energy density, P is W times rho. And then if we think about the known forms of matter in the universe, so we have matter, which corresponds to W equals 0, radiation, which corresponds to 1/3. And by now, from what we know, probably there could be this what is called spatial curvature that is equivalent to W, which is minus 1/3. And if we have an accelerating universe, whether it's cosmological constant, inflation, dark energy, whatever you want to call it, then W is practically -1, or maybe it's slightly above -1. Now, why do I care about this? Because in order to limit the allowed energy momentum tensors that we consider, we devised what is called the so-called energy conditions. Energy conditions, they have various names: a strong energy condition, weak energy condition, et cetera, et cetera. So the most celebrated one is what is called the null energy condition. which says that this W has to be greater or equal to -1. So originally, when the singularity theorems were proven, we knew about matter and radiation. So we even had stronger requirements. But now, okay, now I think that no one will have a problem if we say, okay, we're requiring. Oh, sorry, we're requiring the null energy condition. Now, in general, if we don't want to consider any type of fluid approximation or any such thing, then the null energy condition states that K mu are null vectors, okay, and the null we require that the contraction of the energy momentum tensor with any future pointing null vector, as written here, is greater or equal to 0. This is the null energy condition. Okay. What I mean by that. Why is that relevant, this condition? Because, okay, let's consider a congruence of geodesics. So I have here, a bunch of geodesics that propagate. So I have a cross-section, infinitesimal cross-section of geodesics. Just a second, guys. So if I look at this cross-section of geodesics, then, these geodesics, according to the metric, they expand or contract, and I can define their expansion as as 1 over this area times the derivative of the area with respect to the affine parameter that is parameterizing these curves here. Okay, lambda. Okay, this is called the classical scalar expansion. Now, why do I care about that? Because when we want to prove singularity theorems, there are many theorems in GR are based on this so-called Raychaudhuri equation. Okay, so if I write the Raychaudhuri equation for these null geodesics, the geodesics which propagate on propagate on the light cone or any type of null geodesics, then the Raychaudhuri equation is given here. The derivative of this scalar expansion is -1/2 the scalar expansion squared times this contraction with the Ricci tensor. And using Einstein's equations, I get here the energy momentum tensor contracted with these null vectors. This is not the most general form of the equation. In principle, you can add here terms that include the shear or torsion of these geodesics. For simplicity, I'm just concentrating on these 2 terms. So the derivative of the scalar expansion equals, something, the negative squared of the scalar expansion plus this energy term. Now, here is where I need the null energy condition. If I assume the null energy condition, then I know that theta prime for sure is more negative. I can drop this term, and then theta prime for sure is more negative than this term. And then this is an inequality that I can integrate. And then you see that for a finite affine parameter lambda, you get that if you started with a negative expansion, meaning that the geodesics are contracting, at finite lambda, you get a caustic. Okay, we get a caustic. So we get that this geodesic that should never meet at a single point. And basically, this is the basis of all singularity theorems. Practically all singularity theorems are based on this Raychaudhuri equation. There is more mathematical work to do to reach the conclusion of the theorem, but this is a major step. So that's why if I have a energy that fulfills the null energy condition, I get a singularity, while if I violate this null energy condition, then perhaps there is a way to avoid the singularity. Is that clear so far? Okay. So what are the results that were used using this null energy condition in the Raychaudhuri equation? So black hole singularities, Big Bang singularity, the classical area theorem of a black hole, the fact that the black hole can only increase in area is also based on that. And there are a bunch of other results. I won't go on into all of them. The point I wish to make is that they're useless in the real world. Now, of course, this is a bit provocative, but why are they useless in the real world? Because the real world is filled with quantum fields, and quantum field theory violates this classical null energy condition. So I wouldn't say these singularity theorems are totally wrong, but anyway, this is a major caveat that, we're using a classical null energy condition while we know that quantum fields violate this null energy condition. So let's try to move towards, instead of classical GR, a semi-classical gravity. So in semi-classical gravity, what do? This is something we do every day in cosmology and in black hole physics, et cetera, et cetera. We say, okay, we have a classical background that is fixed. On top of that, we have quantum fields. And then, so we don't quantize the full metric, but we allow for perturbations of the metric, and the perturbations of the metric are allowed to be quantized. Okay. And that's, for instance, how we calculate inflationary observables. We say, okay, we have the metric perturbations, they fulfill some commutation relations, and then we derive the power spectrum of inflation, et cetera, et cetera. So when we want to treat this semi-classical approximation, so now because we have quantum fields, so the energy momentum tensor gets quantum corrections. In principle, when we will now write in the Raychaudhuri equation or any other equation, we will write this energy momentum tensor. So in principle, we're assuming that it is to all orders in H bar, that I've calculated all order corrections in H bar, but only first order in G. So I don't have any corrections which are of the order of G squared, et cetera, et cetera. Okay. And once I consider such an approximation, such a semi-classical analysis, then, for instance, one of the most interesting things that I'm getting are all these black hole thermodynamics. So I'm getting Bekenstein's generalized second law of thermodynamics. Hawking radiation is based on such calculation. In cosmology, I have inflation, the theory of large-scale structure. These are all celebrated examples of semi-classical analysis.
Ido, a question. So
yes.
Do we know anything about such, if you can go to the slide before, I mean, such corrections in G, do we know anything about them? I mean,
whether you have a G squared, you mean?
Yeah, I mean, do we know anything about such higher order in G corrections?
What is it that's being perturbed? G?
So, right, you can calculate quantum corrections, so you can calculate loop diagrams, and then if you have gravitons, then presumably you'll have higher order corrections in G. Okay. Yeah. So this, yeah. And in that sense, I'm not looking at any corrections that include something which is G squared only. So, and it's, yeah. I'm just so I'm calculating quantum corrections that are only that in principle, of course, in practice, no one calculates to all orders in H bar, but that in principle, if you want to calculate nth order corrections in H bar, you can do it, and that the analysis will still be valid. That's what I'm saying here. Yeah.
Okay.
Okay. Right. So, okay. So the Bekenstein-Hawking, let's discuss that. So, right, Bekenstein in 72 showed that we have, because black holes have entropy. So if we consider a black hole and matter outside the black hole, then we have the generalized entropy, which is the area of the black hole, plus the matter entropy outside the black hole. Okay, now this is, of course, a fascinating formula because, as you can see, it consists of all fundamental constants of nature. And then what we have is this generalized second law, which says that the generalized entropy should only increase rather than just the matter entropy. Okay, now let's say in modern language, this matter entropy is the von Neumann entropy of quantum fields on one side of the cross section of the area. So if I have the horizon, so I just take outside the horizon up to infinity, I'll have the entanglement entropy of the quantum fields. A is the area of the horizon. And of course, the lessons that we've learned is that black holes are thermodynamical objects. They have entropy, temperature. They radiate away and disappear. And that is also one of the reasons we are considering this so-called black hole information paradox. That the information that fell into the black hole and then it evaporated, and the evaporation is not sufficient to account for all the information that went into the black hole. So this is the so-called black hole information paradox. Now, one property that maybe is worth noting is that an interesting thing is that this entanglement or von Neumann entropy diverges. So what is nice is that these divergence, when I consider the generalized entropy, okay, can I stop just a second and close these pings? Okay, sorry, everyone will see that I'm using WhatsApp web, but still. Okay. Okay, sorry, back to business. So the generalized entropy is finite, okay? Unlike the entanglement entropy, the generalized entropy is finite, okay? And this is, of course, a very nice physical property to deal with finite quantities. Okay, so now, so if we want to discuss this semi-classical analysis, so now we can consider the generalized entropy, not only of black holes, but also locally, in the sense that, okay, here I have a Cauchy hypersurface sigma, and then I split it, and then A is this infinitesimal area, and the entropy, this matter entropy is this entropy here on this part of the slice, the von Neumann entropy on this part of the slice. This will be the generalized entropy. And okay, so I can define it also in this way. I don't need anymore this black hole. And then there is the proposal. There is a proposal mostly driven by Busso at Berkeley, which says, okay, let's take classical results in GR, okay? And then, which, as we said, they are not valid anymore in the presence of quantum fields. Replace, instead of area, replace 4gh bar times the generalized entropy, and see whether we can derive new results by that. So basically, the idea is to extend classical GR results to the semi-classical regime, where I include quantum fields. And this approach is very successful. So people managed to derive what is called the generalized second law for cosmology. They got modified singularity theorems using this generalized entropy instead of the area. So for instance, they got one results where you don't have to assume some, I think, compactness property of space time. So they could prove some theorem, I think, in closed universe also, which was not possible before that. And we also had recent advances in the black hole information paradox using this approach. So,
Ido, can you explain that again? What are you replacing with what? I mean, the area.
So I want to replace the area with a generalized entropy. Okay.
So what? Could you explain again? Why are we doing this? Like
because
intuition?
because I know, because I have many examples in GR which work classically, but they're not valid, or at least not rigorously proven once I include quantum fields. And I would like to see whether the results are still valid once I include quantum fields, at least semi-classically. Yeah.
And to this, you're going to add the matter entropy, the von Neumann entropy.
Right. So for instance, we'll get basically the heart of things is that now, there will be some modification, the Raychaudhuri equation, or not exactly, but something similar to the Raychaudhuri equation will be modified. Okay.
Okay, thank you.
Okay, so, right. So what do I do? So if I replace A by the generalized entropy, so now the expansion changes. What I call the classical scalar expansion now becomes this quantum expansion, which I denote by capital theta. Okay, which is basically, so if I look at this hypersurface, so you see it's parameterized by this coordinate y, and here I have all these null geodesics. Ki is a null vector, Li is another orthogonal null vector. So I can choose an embedding function v of y, which is, you can see it here in this red thing. And then I'm asking, okay, so by deforming this surface, how does this embedding function, how does the generalized entropy changes? So this is the definition using functional derivatives. a much more pedestrian definition is that this quantum expansion is the classical expansion plus this term. So the derivative, so, you know, for GH bar divided by this infinitesimal cross section times S prime. Okay, the derivative of the matter entropy along this affine parameter. Okay. Now, once you use that, then, you know, again, this has been used several times, this so-called island proposition, you know, quantum, basically, so now when theta equals 0, you have a quantum extremal surface, and they were crucial to show, for instance, these recent advances that black hole evaporation is unitary, and in various other works. Okay. So what are we going to do with that? Okay, we have the quantum focusing conjecture, which is the following. So, right, we said that the Raychaudhuri equation, if I assume the null energy condition, I get that theta prime is negative semi-definite. So now
Ido, sorry, can I ask a question about the former slide?
Yes.
Just a second, just to understand. So this theta is this expansion is the property of a geodesic.
Of a congruence,
right?
of geodesics, yeah.
So S prime, I'm just trying to understand the plot in the upper right side. I mean, what is this area? What is this B? This is the congruence. This is a kind of a slice of the congruence.
Yeah, this is like I'm plotting the area of the congruence. Yeah. Okay, and I will deform it. Okay, so I can deform it along Y or orthogonal to Y. And I will, so yeah, so then I will have a contribution due to the derivative of the matter entropy of the von Neumann.
How? So this is, so just to understand, what is this entropy actually in relation to the plots in the upper right side?
So
it's the von Neumann entropy that you get by tracing out all the degrees of freedom outside of this B, or what?
Right, yeah, so, okay, so, right, so we define this entropy as, you know, the area of this cross-section plus this non-local von Neumann entropy from here to infinity, okay? Yeah. So if you want to think, you know, so supposedly this is like the inside of the black hole, this is the outside, so we trace over, you can trace on one of the sides and get the entanglement entropy.
Can I ask a question?
Sure.
So, but you're talking about quantum fields here as the matter entropy, right?
Sorry?
You're talking about quantum fields.
Right.
So when you talk about the area and that, you're actually talking about a field that is bounded by this area. I'd like to understand the connection between the geometry and the field.
Okay.
Because you talk about a congruence and
right.
about geodesics, and then you talk about a field, and where do they match up?
Okay, so okay, so here, if this is like a sigma, capital sigma is a Cauchy hypersurface, okay? So I have fields everywhere in space-time, okay? Now I'm saying that I'm slicing the Cauchy hypersurface here, right? So here I'll have an area, and I still have, so and then I take the entropy of these quantum fields that are everywhere in space-time along this, you know, this outside part of this Cauchy hypersurface. Yeah.
So if you go to your next diagram that Chachla asked about with the B, so there are fields that are bounded inside and outside of B.
Right. So I have the area, you know, let's say this is the surface. So this is right. It has some area, and I have the fields all the way to infinity.
Yeah.
Yeah.
Okay.
And then I deform this surface. So, I mean, the complication here is that because this S is non-local, right? Everything here looks local, but S is non-local, and therefore also SGen will be non-local, and that's maybe difficult to visualize. But the idea is that, okay, I will deform this surface, right? This deformation, right? So classically, of course, this deformation affects the classical expansion. But then it will also, I will also have a contribution from the quantum fields, the derivative of the entropy of the quantum fields.
And the entropy is entanglement entropy between fields.
Right.
On top and below the surface, or like on one side.
Along this, as I said, yeah, the entanglement entropy from here to infinity. Yeah. So your reduced density matrix is this row out, which describes the state, you know, from here.
Thank you.
Yeah. Okay. So So basically, what I'm okay. So let's go back. So the quantum. So based on the idea of the Ricciardo equation, that in the Ricciardo equation, if we assume the null energy condition, we are guaranteed that theta prime, the derivative of the classical expansion, is negative. Here we don't assume that anymore, but we're assuming that we're looking at the derivative of the quantum expansion. Okay, so basically, okay, if you want to look at it as functional derivatives, then you have off-diagonal version, which y1 is not equal to y2. And then this has been proven in the original paper by entropy subadditivity. And then or you can look at the diagonal part, which is y2 equals y1. And then you can write it simply as the derivative of quantum expansion along the affine parameter. And the conjecture is that this is always negative. This is a conjecture, okay? And this, of course, has not been proven. It's a conjecture, but we're treating it seriously, and people have used it in various cases. And we also, okay, I'll say what we think about this conjecture. So, okay, so basically, you can treat this conjecture as sort of an energy. I will show shortly why.
Can I ask a question, though? So, yes. So this should hold for any state, any quantum state of the field?
Yes.
Or is it only for vacuum or something?
No,
or?
no. The conjecture is that it's true for any state. Yeah.
Okay.
Yeah. Yeah, of course, if we deal with vacuum, things become simpler, right? Okay, so basically it's a sort of an energy condition in the presence of gravity, and then already in that paper or follow-ups, you can derive from it again some well-known, like the Busso entropy bound or various other entropy bounds. You can again get some form of the generalized second law. And what is interesting in our case is that you can get this quantum null energy condition. Okay, so what is the okay? I think I already said what I want to say. Okay, here. So right. So the quantum null energy condition. What is the quantum null energy condition? So let's look at the quantum the derivative of the quantum expansion. Substitute into it the classical Ricciardo equation. Okay. Now, so here you see it looks like an energy condition in the presence of gravity. Okay. And now we can look at various limits. So let's say we take h bar to 0. That should reproduce the classical null energy condition, and it does. You get that this term drops out. And if I consider geodesics with zero expansion, I simply get the classical null energy condition. Now, the quantum version is that actually I don't take h bar to 0. H bar is non-zero, but I look at the limit where the classical expansion vanishes. Theta goes to 0. So if you look at the inequality and we move sides, you see that you get an energy condition which does not have G in it. So it's independent of gravity. And this is it has h bar, so this is the quantum null energy condition. So usually we try to look at quantum fields on flat space and try to, from it, deduce things about quantum fields in curved space and about quantum gravity. But here actually we went the other way around. We started with semi-classical analysis, and assuming this conjecture, which is certainly a conjecture, we got a statement which is a field theory statement. It doesn't have G in it. And if its a statement is true, it should be true in Minkowski space in the absence of gravity. And then I should be able to prove it using field theory techniques alone in the absence of gravity. Okay, so this is the quantum null energy condition. This condition is weaker than the classical because S double prime can be negative. Okay, so it's a weaker condition. And this has been proven in field theory. in various rigorous and various, whether it's just vacuum or just conformal field theories or in general, but it has been proven in field theory, okay, in various setups. But in most of these proofs, these are very long proofs, yeah? While I derived this condition in 2 lines. So that's let's say, the success of this idea that if the conjecture is true, you can get an energy condition in 2 lines where, from field theory point of view side, I had to use 70 pages to prove it. And so one can think of various things. For instance, it's a conjecture, perhaps it's wrong. So what people try to do is to say, okay, let's think of a more restricted version, which says that only where the quantum expansion vanishes, so capital theta is 0, only then we require that its derivative will be negative. So this is right, this is restricted. I'm not requiring that everywhere theta prime is negative, but just only at points where the quantum expansion vanishes. Now, this has been proven in certain scenarios, so it's not just a conjecture anymore. And the nice thing about it is that, it still gives all these recent results regarding the generalized second law, singularity theorems, et cetera, et cetera. And so what we're going to do is, okay, we are allowed to consider other limits than what has been considered so far. So let's consider, again, this the limit where the quantum expansion vanishes, not the classical, but the quantum expansion vanishes. So now I will have this quantum focusing conjecture, but I will have this additional constraint that capital theta vanishes. And if I'll substitute it into the quantum focusing conjecture, I get this condition. So notice again, I get an energy condition that is independent of G. So it's again a field theory statement. Now, this field theory statement is stronger than the quantum null energy condition because of this equality, then this term is positive, semi-definite. Even though it has a minus sign, this term should be positive, semi-definite. So this is a stronger condition. So we use the same game, the same idea, and got a stronger energy condition. Several more details to mention is that this is in 4 dimensions, of course. Yeah, here I'm in 4 dimensions. In any other dimension, this is the general result. So in D equals 2 or 3 dimension, this term actually vanishes, and we're left again with the original INEC. If I take due to infinity, I get some other modified version. I don't think there's a point in discussing that further. So what can be the outcome of this result? So one thing which I'm trying to work very hard on now is to actually try to, again, use field theory and prove this in Minkowski space-time. If this is wrong, or if I'm not able to prove, then it means that the Q of C and its restriction. So if I have a counterexample, let's put it this way. If I have a counterexample, then it means that the Q of C and the restricted version are only perturbatively correct. And then if I want to have another conjecture, I have to modify it and add higher order terms so that it will hold. It could be that all the cases are redundant. It could be that whenever theta vanishes, it's only the redundant case of theta equals S prime equals 0. And then these are exactly the points where the QNEC, the original QNEC, is saturated. Or it could be that the approach is incorrect, or not incorrect, but okay, that when we're writing this, it's not only first order in H bar, but also, so it's not to all orders in H bar, but only first order in H bar. Okay. So these are the possible implications of this result. Now, why don't I have a proof yet? So the thing is that I have to consider now, even though I'm in Minkowski space, so there is no gravity, I have to consider something like spheres, or anyway, curved surfaces where this classical expansion is non-zero. And then to plug it into the inequality and see whether it holds. Sadly, it seems that it's difficult. So usually we know to write what is called the modular Hamiltonian, which is related to the entropy, only in cases of, flat surfaces. So it seems that it's not entirely true, and that's what we're trying to do now, that if you have a bifurcating Killing horizon, then probably you can still write this modular Hamiltonian. The modular Hamiltonian is related to the entropy, and then eventually we will be able to prove it, hopefully. So this is where we're at the moment, that we're trying to deal with these things and prove the theorem. Maybe not the theorem, try to prove the condition, sorry. Maybe some indications that the conditions is still true are the following. So if we look at Cassini's paper about proving the A theorem using entropy, so you can see that in 4 dimensions, and if you consider spheres, then you see that he's getting basically the vacuum version of what we have. Okay, so here we have the energy momentum tensor, and here he has vacuum. So this is one indication that that it's true, at least in some restricted sense. And then the other thing is that, okay.
Ido, excuse me, Ido, Cassini's S is entanglement entropy, right? I mean, it's not, yeah, okay.
Yeah. Whenever I write S or S out, I mean entanglement entropy of the quantum fields. Right. So another indication that maybe what we're doing is okay is that, okay, it seems that at least for perturbing these flat surfaces, we have the modular Hamiltonian for these perturbed surfaces. And then that's why it seems that, okay, at least for these perturbed surfaces, we will be able to calculate the different quantities in the INEC and see whether it holds or not. Okay, and these surfaces already have non-zero expansion, so it will work. At least perturbatively, we can do
it. Ido, can I ask another question? So I just want to understand. So the surfaces that you're talking about, and now we're talking about deforming them, they're always cross sections of the congruence of geodesics. So they're always, you think of them as having infinitesimal area?
Yes, A is infinitesimal, yeah.
Okay.
I mean, okay, maybe I should point out that here I'm already discussing Minkowski space, yeah, just to be clear. Here, this is already no gravity here, yeah? When I'm discussing a proof, I'm discussing about the field theory proof, so now I'm saying I'm in Minkowski space, this is the light cone, etc., yeah, just to be clear. Okay, so in the few minutes that I have left, I will now say maybe a few more implications about the INEC, and I will conclude. So one thing that you can think of is, okay, here I write, if I go back to the INEC, I can write it in terms of geometric, so I can use again Raychaudhuri equation to write it only in terms of geometric properties. So, and here I have G again, but anyway, I have you see, I have here a limit on the geometry of space is limited by this second derivative of the entanglement entropy. This is just reshuffling the terms. The nice thing is that if I use the classical Raychaudhuri equation and the definition of theta, I get that these quantum extremal surfaces are not just extremal, they're maximal. Okay, I don't just get that the first derivative of the generalized entropy is vanishing. I get that if the INEC holds, I must have that the second derivative is negative. So these surfaces are not anymore extremal, they're maximal surfaces. Okay, so that's one implication to think about.
What would it mean?
This I don't know yet. Either it will mean that it's totally wrong, or it will mean that, okay, I'm not, that it's maximal. This is a stronger result than extra.
But I mean, if it's maximal, what does that imply?
So it means that the entropy, the generalized entropy on the surfaces really reaches a maximum that you cannot, a local maximum at least that, yeah. Let me just say that the major problem is that, in all this discussion is that examples where I do know the form of S, what is the entanglement entropy, some explicit expression that I can manipulate, are very scarce. There are very few examples. This is the major setback in all this discussion. So I can write some generalized results, some general results, but in practice to feel what I can do with them, so far not too much. Okay, so further implications. So actually, since you know, this conjecture is a conjecture which we don't know, it includes gravity. So maybe we should consider, on the other hand, the QNEC has been proven. So maybe we should consider the QNEC as the fundamental property. And the idea is that I want to try to get some quantum Raychaudhuri equation. You know, if I can get the quantum Raychaudhuri equation or inequality, it will be great, right? I can try to solve it. So if we consider the QNEC as the fundamental property, I can actually get a different inequality, which is that theta prime is not always greater or equal to 0, but smaller or equal, smaller or equal to this thing. Now, this now looks a lot like the original Raychaudhuri equation, right? I have here theta squared, I have here a square term, and then depending on the signs, this can be negative, positive, anything, which looks a lot like the Raychaudhuri equation without assuming any energy condition. So yeah, and this classically it reproduces the classical limits of the Raychaudhuri equation, then the QNEC always holds. So perhaps this is a more proper statement rather than the original quantum focusing conjecture. So let me summarize. So basically what we have learned is that from semi-classical gravity, we can derive field theory results in a very simple manner in 2-3 lines, okay? We got an energy condition that is based on first principles. I did not assume here, the original energy conditions were based on familiarity that, okay, I know about matter and radiation, so let's devise the condition that they fulfill. So here I got it from first principles. We still need to do we still need to prove this INEC. And as I said, I listed, you know, some possible implications. It will be nice maybe to use it in cosmology. Maybe I have a modified Raychaudhuri equation, then I'll have modified Friedmann equations. And of course, ideally, if we can have a full geometrical description of all this, right? So far, I still needed to separate this. I had only one inequality of the quantum expansion related to the area and the entanglement entropy. And it would be nice to have a full set of equations rather than, or full geometry rather than just one equation. So thank you.
Thank you, Ido, for a very interesting talk. So any questions?
I have an unscientific question.
Yes.
If you can go back a slide.
Okay. Yeah.
What's the picture?
I think this is Bryce.
Bryce.
Yeah, Bryce Canyon. Yeah. This is one of the most beautiful places in the world. You really have to go there. I was there as a kid when I was 10 years old, and I remember it as amazing. And then 2 years ago, I went there again. It was still amazing.
It distracts from the lessons.
What?
It distracts from the lessons.
Yeah,
but
yeah.
Okay.
So
yeah, the other, yeah. Well, so I was at sabbatical at Berkeley for 1 year, and all these pictures are from all the different trips and whatever that we did back then. It was okay. Originally, the talk was some colloquium talk here that apparently I have to give after returning from sabbatical. So it was a good excuse to give many pictures and physics talk together.
So quantum Raychaudhuri equation.
Yes. Yeah.
Would have. I mean, the thing that's quantum here is the H bar related to the generalized entropy. So what that would be relating the expansion to the change in the field boundaries, entropy. Trying to understand what it would actually mean.
So I'm not sorry. So you're asking what would the quantum Ricciardo equation mean?
Yeah.
Okay, I think physically it will mean that now you have an expansion which some semi-classical expansion which takes into account quantum effects. And I think it can have interesting implications because, for instance, in cosmology, let's say we want to have a bouncing universe, okay? So if you want to have a bouncing universe, then usually it implies violating the classical null energy condition. And I think it will be very interesting if we can construct a bouncing model that violates the null energy condition, but does not violate the quantum null energy condition. I think this will be a strong statement to say that these solutions are reasonable. Okay, because currently the analysis is always done with respect to the classical condition, and you get a never-ending discussion, a never-ending argument, because people say, we found this instability, but then people say, no, we checked it perturbatively and this instability is gone. And then it becomes a matter of personal tastes. When we don't like usually to have personal taste as some decisive factors in our physical theories. So yeah, so for instance, one thing that we're trying to think about is, okay, so if I have a modified Ricciardo equation, it means a modified Friedman equations, which means I open up, more solutions are possible because I have this extra quantum term. It could be that this quantum, so of course, naively, this quantum term can be very negligible, but not necessarily. So yeah. So the idea is, if I have a quantum Ricciardo equality or inequality, then then it will mean I will be able to revise all these well-known results and see whether there are loopholes there.
But in the simplest form, it means that when you have geodesics and you trace them to find the expansion, it's going to be affected by the fields.
Yes.
Which is common sense, what it should be.
Yeah.
What about implications for the interior of black holes of the this quantum Ricciardo equation? I mean, or constructing traversable wormholes, stuff like that. I mean, that also usually involves violations of energy conditions, right?
Right. So excellent. Well, not excellent because I don't know exactly the answer, but a very good question. So yeah, right. So as far as I know, right, so people recently did manage to construct traversable wormholes, and the requirement was that you have this quantum matter that violates the classical null energy condition, but not the quantum one. And that's why people trust this result. I should say that at the end of the day, this analysis is semi-classical. So implicitly, we are assuming that, this infinitesimal area is still much larger than the Planck area. And, if we try to approach the singularity or, Planckian curvature, then of course, this analysis is not valid anymore.
Okay. Any more questions? Okay, if not, let's thank Ido again.
So yeah, it was really nice. I hope you enjoyed it. Yeah.